Okay, welcome to this video that is a primer for conducting an assignment or quiz on estimating the coefficient of expansion and a delta T factor for material that we extract from an energy versus separation distance curve. Some background on the idea is provided here. We'll first recall the energy versus separation distance curve and think about what might be related to the property of matter that affects this curve. So as we've seen before, hopefully you recall that things like the bond type might affect the strength of the bond and ultimately the depth of the well in this graph, which represents the bond strength, of course. We also know that the bond number, or the number of bonds, so if we have this graph representing several bonds for an ionic compound with with high coordination number, all of these bonds could affect the graph. But this is more obvious when we consider things like single bonds all the way through to triple bonds, because we recall that single bonds are long and weaker, and triple bonds are short and stronger, and so the depth of the well in the curve would respond. And of course the atom type, the atoms in question, which is of course the Z number for their position in the periodic table, implies something about their size, and very small atoms might bond very close to one another, whereas very large atoms are likely to have longer bond lengths. Okay, so what else can we say about this curve? Well, we know from the Heisenberg uncertainty principle that we are not allowed to know the position and speed of particles, very small particles, when they approach the size of an atom. So what this means is that if we want to say that the actual bond length is exactly the minimum in this well, that would imply that we know the exact position of the atoms in that material. And so this breaks the Heisenberg uncertainty principle, and for that reason, we know that even at absolute zero temperature, that bonds like these in question vibrate a little bit. Quantum mechanical handling of these bonds as well shows that there's vibrations present as well. So what this means is that if we're to consider a temperature condition that even at the lowest temperature of absolute zero, that our analysis would need to consider a y-coordinate line, if you want, that is above the minimum. And so we would have intersection points of that analysis line with our energy versus separation distance curve. Okay? And so it might follow, therefore, that the average of the x-coordinates of these intersection points, which we could represent as R min and R max, so the average of R min and R max, represented by the line here, might represent the average bond length at absolute zero. And you can see when we consider going to hotter temperatures, it looks like we are considering raising our kind of line of analysis here to a higher y-coordinate value. And that follows from the simple idea that temperature affects the energy of the system and therefore the energy value in the graph. So in this analysis here, U is in fact potential energy of the bond in question, and potential energy is going to be our analysis is going to affect where we would consider intersecting this potential energy curve based on the temperature in question. And so as we raise the temperature, we provide more motion to atoms. That is, in fact, what temperature is motion of atoms and molecules in matter. And so the collective average of all those atoms in matter and their kinetic energy correlates here to the temperature. So you see that with T here. And so if we know Boltzmann's constant and temperature, we can determine the energy value, which would respond to how higher we climb on this graph for our analysis. So if we go from absolute 0 to room temperature, we now consider two new intersection points. And you can see here that the average or the midpoint of those is now shifted to longer separation distance, represented here by the blue hash mark. And then if we raise the temperature even further from room temperature to an even more elevated temperature condition, we'd expect that average bond length to extend further. And so those new intersection points are going to have a midpoint that's further to the right. Okay. So what we've learned here is that the idea of applying temperature to matter is going to affect the average bond length. And this suggests something about the actual dimensions of the macroscopic object, provided they're represented by the bonds that we've got in our graph. So for some matter like steel of some initial length L naught with shorter bonds between all atoms in the matter, we'd expect that as we apply higher temperature that the bonds would stretch, therefore, uniformly throughout the matter, and this would lead to a change in the dimensions of the object. So this is in fact true. Most objects expand when heated. And so here we see that there's a linear expansion by an amount, it's lowercase delta, or sometimes shown as delta L, the change in length. Okay, so those two are often used. And delta L, therefore, is equal to lowercase delta, which is, of course, the final length, all the way down, minus the initial length over here. Okay, very simple idea there. And we can see that that's somehow related to the bond curve from the previous slide. The relationship there can be inspected in a linear fashion for a linear expansion coefficient or a volumetric coefficient. So a delta V, the change in volume for three-dimensional expansion, would of course be the final volume minus the initial volume in our analysis, or V naught if we're using the same terminology on the slide. Okay, both of those are correlated to the temperature through a constant, an alpha constant. So in the linear version, the delta L, change in length divided by the initial length, can be correlated to the change in temperature with this constant alpha L, which is the linear coefficient expansion constant alpha L. Analogously, if we have volume information, the change in volume relative to its initial volume is related to the change in temperature by the constant alpha V. So these alpha values are specific to certain types of material and are often tabulated for us to help us understand how much matter might expand or contract, either linearly or volumetrically or both. An application of this is found in some old technology, like the mechanical switches in old toaster ovens, where a brass layer might be applied as a sandwich structure to a steel layer. And the brass layer here is known to have a larger linear expansion coefficient than brass. Than steel, apologies. And so this would mean that the brass would want to expand more linearly than the steel, and the only way to accommodate that shape change is to provide a bend in the structure, and that could affect some sort of a mechanical switch to kind of move a hook out of the way, for example, and allow something to release. So this was often the strategy in the switches, the mechanical switches that were temperature sensitive inside old toaster ovens. Okay, so to help us with our exercise, we're going to take a simpler approach to the mathematics behind the potential energy versus separation distance in the information we have. So your Excel sheet will have some atomic spacing data already listed for us, and some material data already listed for us. So you could think of this data already as experimental data, measured by some microscopic technique. What we're going to do is try to populate fit data or theoretical data positions next to that. We're going to estimate that knowing that the potential energy coordinates in our graphs are the sum of two components, the potential energy due to attraction and the potential energy due to repulsion. We've seen that idea before. This time the equations are a little different to one, accommodate units like nanometers for the separation distance, and two, to be very specific to certain types of bonds. So you'll see here that the exponents are often fractional, and the units are therefore going to be very complex. So regardless, the mathematics help fit actual data quite nicely, as we'll see, and we'll use that to help us. So the first component, the potential energy due to attraction, is simply a constant A, tabulated for us, divided through by the separation distance r raised to a power. Okay, so that is the n value here is a constant as well. So these two values, a and n, do not change with temperature, and they do not change with separation distance. Okay, we're going to see that sort of fractional amount, of course, having a negative sign to give us a negative territory in the u versus separation distance, the potential versus separation distance curve, and we're going to see positive values from the analogous equation in the repulsion curve. So that is, in the repulsion curve, we've got to have a constant b for the numerator and an exponent of m for that component of the graph. And so the mathematical sum of these two is what's going to give us the potential energy information. So U here is, if you want, the theoretical information that we can determine, provided that we have these constants. Okay, so your exercise will be first to program this cell here to calculate the potential energy given the constants that were provided to you in the Excel sheet and this separation distance r. Once you've programmed this cell, you should see that the value in here should closely match the data. If not, perhaps something's gone wrong with your bed mass or your parentheses in your programming of the Excel. So if things look good, you'll be then directed to permutate that equation down the row. But notice, of course, that we want some things held constant. So these constants down below, you want to hold constants with things like the dollar symbol in Excel. So for example, if one of those was positioned in cell E4, you would want to lock them in your first equation with dollar symbols, or the F4 key, which provides those dollar symbols, and then permutate that down. So the only one that you want floating is, of course, the R value in your equation. Okay, so that, again, should give you a whole bunch of data all the way down, and every one of these cells should match the actual experimental data quite closely. If not, something has gone wrong. You can also inspect that but in a graphical format. So here, maybe your experimental data, the initial column of information is shown in one line, and then your theoretical data might be shown as a second line or a fit, and these curves should be very closely overlapping with one another. If not, the programming of the Excel sheet is incorrect. Okay, so our next exercise is going to be to try to pull out some information on L naught and use U naught for giving us a new temperature condition. So let's first speak to L naught. So this is going to be temperature at some low condition for us. We're going to assume that the equilibrium atomic spacing here is going to be very close to the energy minimum in this curve. As you can see here, that when we're at very low temperatures, the average R naught here is going to be close to the minimum here. So our first exercise is going to be to populate the first cell here with the x coordinate for the minimum. So this can be found by using the min function on your U theoretical column of info, and then looking for that value and finding the R value to give us this 0.285. Okay, so that is this value here is in that first column of information somewhere down here, where this value and this value are at a minimum. Okay. To calculate the bond energy now at equilibrium, we can solve for R, provided that we know the U value. So if you use the U theoretical and solve for R, we can calculate R. So that's what the next slide has done for us. Once we know the U equilibrium, so this is the minimum value, you can use this equation, which is the solution for solving for R from that previous one. Solve for R. So saving you a bit of time there on the arithmetic, and then we can calculate the R value. Okay, and that's going to give us a value that is very close to the x coordinate of the minimum, but technically different given that we've calculated it. Okay, so that gives us this second value here. Okay, the next part of the exercise is to use those two values, specifically the bond energy value, to help us with a temperature condition for the next part. So we're going to assume that the thermal energy associated with the increased material temperature is going to be 20% of the bond energy. So that is, we're going to climb here a value that's a fifth as deep as the well. So our new energy value, U, at some temperature condition is going to equal the U of equilibrium, so that's the minimum. That'll be a negative value, plus the absolute of 0.2, 20%, times that U equilibrium. So this should add a fifth of the equilibrium value to where we were. So we should climb from down here up about a fifth of that distance. And that'll give us a new analysis region here. Okay, so roughly 35 negative electron volts plus a fifth of that, so add about 7 will be the outcome for material A. Material B, C, and D, which are tabulated to the right, are going to be different in their U EQ, and you'll add a different amount than 7 electron volts to get the new entry down below. Okay, so with that, we're then ready to do some of the easier steps, which is to now say we know the y-coordinate that represents our warmer temperature of the material, and we simply want to find the R low and the R high value so that we can determine an average at that warmer condition, at that condition where added thermal energy is included in the material. So we simply go to our table of data and we want to inspect for the values that are as close to this as possible. So our energy curve, as you recall, should have 2 intersection points, and we should be able to find this value twice, an R min and an R max. So as we walk down this data, we're looking for minus 27.74 electron volts, very large numbers when our spacing is very short, and we're getting closer into the hundreds, and then very quickly we find a value here that's 23.8 negative, 28.5 negative. So our R min is somewhere in between here, and we'll simply just take the midpoint of that. So R min here is going to equal 0.2625 rounded up. to this value here for 3 decimal points. As we continue to longer separation distance, we're going to continue deeper into the well, get closer to the absolute zero condition. So you can see our lowest kind of data point there is about here. And we start climbing the curve, and then we're ultimately going to cross that minus 27.7442 value again. And so our max is somewhere in between here. And for sake of simplicity, we'll just take the midpoint there, and that'll give us this value here. Okay, with those two in place, we can simply take the average and calculate the average R value. So we now have the R value at a higher temperature condition represented by roughly 20% more thermal energy in the material than the depth of our well. And this value, this average R value, better be larger than the R equilibrium that we've estimated from the minimum. With those informations, we have L0, we have L final for the bond, and we can input them into our thermal expansion coefficient equations. So the left-hand side here can be estimated from simply L final minus L naught divided by the initial length, L naught, and that gives us a thermal expansion coefficient product where we have built-in delta T, and without temperature information, that's as far as we can go. So we can calculate this value. Okay, and so that's what we have shown here. And so that's the last entry down below. The last part of the exercise is to be able to identify the material. So given in the first material A, we've told you that material A is a metal. In unknown material B, we've told you that it is a polymer based on covalent bonding. So you'll inspect your curves, your graphs, to look for characteristics that might be associated with metal and metallic bonding. So strong bonding, very high melt points, deep wells. And as we recall, polymers have covalent bonds, which are strong in only one direction generally, weak in the two other dimensions of the material due to intermolecular forces being weaker there, and melt points of polymers are generally lower, and so that would infer lower wells. And so you can look for characteristics like that in the other material curves, B through C, to identify the material class, either metal or polymer. Okay, with that, you should be ready to tackle that exercise, so please do that when you can.